The first images of 3I Atlas entering the inner solar system did not spark excitement. There was no dramatic tale, no expanding cloud of gas, no visual spectacle announcing the arrival of an interstellar wanderer. Instead, astronomers saw something almost unsettling in its simplicity. A single compact point of light, sharp against the star field, unchanged night after night. Even as it moved closer to the sun, Atlas remained visually silent. No halo formed around it, no dust trailed behind. The surface appeared smooth and featureless in every dataset. Hubble, with optics sensitive enough to detect the faintest traces of gas, saw nothing. This absence became the first clue. Months before perihelion, Atlas established a baseline that defied expectations, quietly setting the stage for a mystery that would deepen with time. In comet science, proximity to the sun almost guarantees activity. Heat penetrates the surface, frozen volatiles vaporize, jets erupt, and a coma blooms into view. Yet Atlas ignored this script entirely. Image after image showed no change. The July observations became a reference point, a visual fingerprint of what Atlas looked like before anything unusual could be blamed on solar heating. Scientists watched closely, expecting the first signs of transformation. None came. The object remained stubbornly compact, as if insulated from the environment it was passing through. But motion tells stories that images cannot. Precise astrometric tracking soon revealed something unexpected. Atlas was not exactly where gravity said it should be. By early November, its position had drifted several arcseconds from the predicted path. At its distance, that translated into tens of thousands of kilometers of displacement in a matter of weeks. This was not noise. It was a sustained deviation, measurable across independent observatories. Calculations showed a non-gravitational acceleration acting on a body roughly 6 kilometers wide. The force was small in human terms, but enormous on a cosmic scale. Enough to alter its trajectory significantly over time. Gravity alone could not explain it. The numbers pointed to a continuous push, steady and directional. In comets, such accelerations are usually caused by outgassing, material erupting from the surface and acting like natural thrusters. But here was the problem. There was no visible outgassing, no coma, no tail, no dust. The sky showed nothing that could account for the force the math demanded. When Atlas reached perihelion in late October, expectations peaked. If it were ever going to behave like a comet, this was the moment. Instead, it passed the sun unchanged, compact, sharp, silent. The object then continued outward, setting up a critical observation window. In December, Atlas would make its closest approach to Earth, not dangerously close, but close enough for the most detailed measurements possible. Telescopes around the world prepared for what many considered a decisive test. After that, Atlas would head toward Jupiter, receiving one final gravitational nudge before exiting the solar system forever. There was no threat of impact. The only thing at risk was our understanding. These milestones formed a countdown. Perihelion, Earth approach, Jupiter passage, each one an opportunity for nature to reveal what was really happening. The physics made the mystery sharper. To push an object of Atlas's size off course by such a margin required an immense transfer of momentum. Estimates suggested that billions of tons of material would need to be expelled in a short time to produce the measured acceleration. That level of mass loss would not be subtle. It would create a bright, sprawling coma visible even to modest telescopes. Spectral signatures would light up detectors. Dust would scatter sunlight across millions of kilometers. Yet nothing appeared. The sky remained clean. The contradiction was unavoidable. This was not a matter of interpretation. It was a testable prediction. If the push came from outgassing, then visible evidence must appear. If it did not, the model failed. That clarity triggered an unprecedented coordinated response. From late 2025 into early 2026, an international network of observatories committed to continuous monitoring. Hubble focused on high-resolution imaging. The James Webb Space Telescope targeted the infrared, searching for faint gases invisible to optical instruments. On Earth, the world's largest telescopes rotated through photometry, spectroscopy, and polarimetry, each technique probing a different aspect of Atlas's behavior. Observers tuned their systems to extreme sensitivity. Detection thresholds were pushed to their limits. Even a minor release of gas or dust would stand out. The goal was simple: remove ambiguity. Either Atlas would reveal conventional cometary activity, or it would not. Both outcomes would be decisive. As data accumulated, new anomalies emerged. Photometric measurements showed Atlas brightening at a rate far steeper than typical comets. Instead of following the gentle curve expected as sunlight increases, its brightness surged dramatically, obeying an unusually steep power law. Such behavior is normally associated with violent fragmentation or massive dust release. But again, no coma accompanied it. Color measurements added another layer. Near perihelion, Atlas shifted toward blue wavelengths. This ran counter to everything known about dusty comets, which tend to redden as fine particles scatter sunlight. A blue shift suggested either unusual surface properties or emissions that should have been visible in spectra. They were not. Independent instruments confirmed the result. It was real, persistent, and unexplained. By now, a pattern was forming. Atlas arrived on a trajectory improbably aligned with the plane of the solar system. It was larger than expected for an interstellar object. It moved faster than models predicted. Its chemical signatures hinted at an unusual composition, with metallic ratios unlike those seen in typical comets or asteroids. Water, the backbone of comet activity, appeared scarce. Polarization data failed to match known dust types. Individually, each anomaly might be dismissed. Together, they formed a growing list that resisted simple explanations. Some scientists approached the problem with a strict methodology. Treat each observation as a checkbox. Ask whether known physics can account for it. If not, acknowledge the gap. The emphasis was not on sensational conclusions, but on intellectual honesty. If a natural explanation fits the data, accept it. If it does not, say so plainly. Science advances by confronting uncomfortable results, not by ignoring them. The coming months represent a rare moment of clarity. The criteria are defined in advance. If Atlas develops a detectable coma of sufficient size and brightness, conventional comet physics holds. If spectra reveal gas production at the required rates, the mystery dissolves. If dust appears in quantities consistent with the measured acceleration, the case is closed. But if none of these signatures emerge, then the numbers leave no room for interpretation. The push cannot be natural outgassing. By early 2026, the data will be in. The universe is offering a controlled experiment, one with clear pass-fail conditions. Few astronomical mysteries present such clean decision points. Whatever the outcome, it will force a recalibration of assumptions, either reinforcing what we think we know or exposing how incomplete that knowledge really is. As telescopes track Atlas night after night, the question is no longer whether something unusual is happening. That is already clear. The question is whether we are willing to follow the evidence to its conclusion. Nature does not care about comfort or tradition. It only responds to observation. In this case, the object itself is silent, but the data speaks loudly. Soon, one way or another, 3I Atlas will give its answer. And when it does, the real test will not be about what it is, but about how we choose to listen.